Hello, my name is Java Hiridono, and today we will be discussing Lab 1 of Physics 2212, Charge Tapes. The purpose of this lab was to prepare two pieces of charge tape and observe their interactions between themselves and other objects due to the transferring of electrons. We will then calculate the tape's charge and whether electrons were lost or gained. Fundamental concepts covered include using Newton's second law and Coulomb's law to calculate the charge of the tapes, as well as the electric force acting on them. We will use the measurements taken of the tape to find the ratio between electrons lost or gained to the number of atoms on the tapes. A brief preview of the results shows that the electric charge on the tape was about 1.3 times 10 to the negative 8th coulombs. The charged tapes repelled each other and were determined to both be positive. The tapes, due to being positively charged, were electron deficient by about 8.4 times 10 to the 10th coulombs. To garner these results, I assumed that air resistance is negligible. I also treated each tape as if it were a single point charge, with that charge being in the center of the tape. I also assumed that both charge tapes had equal and evenly distributed charges. In this experiment, the system is charged tapes A and B, and the surroundings are everything else in the room. The initial conditions are that both equal length tapes are neutral before we induce them in a charge. For the procedure, a neutral tape was stuck to a desk. Tape B is then placed onto the desk tape and quickly ripped off, causing the transfer of electrons and inducing a charge. To determine whether this charge was negative or positive, tape B is held up to a known negatively charged pen. Tape B is attracted to the pen, confirming that tape B is positive. A second piece of tape, tape A, is charged in the same fashion. When tape A and B are held close together, they repel, showing they are both positive. The distance between the tape due to the repulsion is recorded to later calculate the magnitude of their charges. And here's some images from the experiment that was done. The measurements taken during the experiment can be used to deduce the following. We get the force of gravity on the tape using Newton's second law and the tape's mass. From here, we recognize that because the tape is not moving, the force of gravity downward is equal to the electric force acting in the opposite direction due to Newton's third law. Therefore, we can plug this force into Coulomb's law, along with the distance between the tapes we measured earlier, to determine the charges on each of the tapes, which is about 1.3 times 10 to the negative 8th coulombs. The number of electrons transferred is equal to this charge divided by the charge of a single electron, resulting in about 8.1 times 10 to the 10th coulombs, making the tapes electron deficient. Next, we calculate the area of our pieces of tape as well as the area of the atom and divide them to get the number of atoms on the tape's surface. We can now determine the ratio between number of electrons lost to number of atoms, which is about 1 electron per 5 million atoms. Shown is the glow script code used to create a computational model of the experiment. As you can see, the two tapes are represented by the blue and red point charge spheres. The electric force is in the green arrow, and the gravitational force is shown by the orange arrow. Just like we stated before, these charges are equal in magnitude but opposite in direction. Some key differences between the physical experiment and computational model are that in real life, the tapes are not singular point charges. The assumption that both tapes carry perfectly distributed and equal charges is not 100% accurate. Additionally, I may have excessively handled the tapes too much, which would cause them to gain back some electrons they lost. A question proposed in the lab was, what if electrons are positively charged and protons negative? Well, our physical observations would remain the same. The charges would still repel because they'd both still be negative and like repels like. Another question was, why is it important we touch the charged tapes as little as possible? Like we said before, the more that the charged tapes interact with other objects like my hand, the more likely it is that they're transferring electrons. Specifically, they're gaining ones they lost to try and become neutral again, which minimizes the repulsion we saw before and would tarnish our results. Some parting remarks are that we can use everyday objects to model electron transferring by looking at the objects as a centralized point charge. Electrons are easily transferred from physical contact. We've also seen how like charges repel and opposites attract. And finally, we now know how to use Newton's laws as well as Coulomb's laws to quantify these forces and electric charges.